Assessments of vegetation, condition, and trend at the scale of Bureau of Land Management land units are essential for informing the land use planning process and evaluating land health. However, the size and variability of many Bureau of Land Management land units makes conducting vegetation assessments at broad scales difficult to impossible using field methods alone. To help to overcome these challenges, the BLM site characterization reports provide satellite-based vegetation and climate data consistently for every BLM state office, district office, field office, and grazing allotment in easy-to-access PDF and PNG reports. In this video, we'll demonstrate each of the maps, figures, and summaries so that you can start using the reports to inform decisions. This tutorial video is broken into a series of sections. We'll start by discussing the motivation for developing the site characterization reports. Next, we will introduce the reporting website. Then, we will discuss the datasets that are compiled in the site characterization reports. We'll demonstrate two examples of using the reports for assessing invasive annual grasses and tree cover change. And finally, we'll round out the tutorial video with some closing considerations. Ecosystems across the western US are diverse, vast, and dynamic, and humans have been involved in the conservation and management of these systems for millennia. The Bureau of Land Management manages 245 million acres of shrubland, grassland, woodland, and riparian ecosystems across the western US, and monitoring these vast vegetation and hydrologic resources at broad scales is a monumental challenge. However, in recent years, satellite data availability, standardized field data, and machine learning modeling have advanced dramatically, and as a result, satellite-based vegetation datasets have become powerful and essential tools for monitoring vegetation condition and change across broad areas. In 2022, Andy Klein-Hesselink and co-authors published Long-Term Trends in Vegetation on Bureau of Land Management Rangelands in the Western United States using these datasets, demonstrating their usefulness for multi-scale resource monitoring on BLM-managed lands. These vegetation datasets are as vast as the western ecosystems that they model, which can make them difficult for resource managers to use. To simplify and streamline the availability of satellite-based vegetation data, our team at climateengine.org has partnered with the Bureau of Land Management to provide site characterization reports for all BLM state offices, district offices, field offices, and grazing allotments in the conterminous 48 states. The site characterization reports are provided alongside the drought reports, for which we have produced a separate tutorial video. While the drought reports are updated every 5 days and reflect real-time drought conditions, the site characterization reports provide a longer-term history of vegetation and climate conditions and are updated yearly. It is worth emphasizing at the outset that these reports are produced using modeled vegetation and climate datasets, and that while these datasets are relevant and useful in management contexts, they should be used alongside additional lines of evidence whenever possible, including field data, ecological site descriptions, photo points, and other local sources of information. Before we get started using the site characterization reports, let's discuss the datasets that the reports summarize. The site characterization reports combine 3 datasets: the Rangeland Analysis Platform, gridMET, and gridMET Drought. The vegetation data in the site characterization reports come from a satellite-based vegetation dataset called the Rangeland Analysis Platform, which provides spatially and temporally comprehensive data from 1986 to present day. The RAP is also a great success story for the BLM's assessment, inventory, and monitoring strategy, as the RAP relies on AIM field plots for model training. The Rangeland Analysis Platform consists of 2 datasets, vegetation cover and production, and we provide both in the site characterization reports. The vegetation cover data are provided as yearly maps of vegetation types from 1986 to 2023 and are updated every year. 5 vegetation cover types are provided: annual forbs and grasses, perennial forbs and grasses, shrubs, trees, and bare ground, and the maps are provided at a 30-meter spatial resolution. That means that each pixel in the image represents roughly the area of the infield of a baseball diamond. For each pixel, a value between 0 and 100 is provided, which represents the percent cover of that vegetation type for that location. The vegetation production data are also provided as yearly maps of vegetation types from 1986 to 2023, and are provided at a 30-meter spatial resolution as well. However, for the vegetation production data, there are only two vegetation types provided: annual forbs and grasses and perennial forbs and grasses, and each pixel represents production in terms of pounds per acre. For more information on the Rangeland Analysis Platform datasets, visit rangelands.app and support.rangelands.app. We also have information on the RAP at support.climateengine.org. gridMET is a climate dataset that provides daily maps of many meteorological and hydrologic variables such as temperature, precipitation, and wind speed in near real time. As such, gridMET is an important dataset for assessing drought and its components. As discussed in our video on the drought reports, precipitation and evaporative demand are two primary variables used to describe drought conditions, representing both sides of the water balance. Both precipitation and evaporative demand are provided in the site characterization reports to provide context about whether BLM land units are becoming wetter or drier through time. For example, even if precipitation is steady through time, a region may become more arid if evaporative demand is increasing due to higher temperatures. For more information on gridMET, visit support.climateengine.org. gridMET Drought provides dozens of drought indicators using the gridMET dataset that we just discussed. Two important indicators are the multi-indicator drought blends, specifically the long-term and short-term drought blends. These are the drought indicators that we use in the drought reports provided at reports.climateengine.org, and are important because they represent two different time periods of drought, which can capture drought impacts to different types of resources. We provide these two drought indicators in the site characterization reports as well to ensure consistency with the drought reports and to provide context about drought as it pertains to vegetation data presented in the reports. We produced a similar tutorial video on drought that you can access by clicking the card in the video. For more information on gridMET Drought, visit support.climateengine.org. Now that we have an understanding of the types of data presented in the site characterization reports, we can explore the reports in more detail. To begin, let's look at an example that demonstrates how the site characterization reports can be used to analyze one of the most challenging resource management issues in the West, invasive annual grasses. In the left-hand column of the reports, you will see maps of current vegetation cover in terms of annual forbs and grasses, perennial forbs and grasses, shrubs, trees, and bare ground for the year of the report, which is 2023 in this case. These maps show spatial patterns of vegetation cover across the land unit for each vegetation cover type. We can see that for this location, there is very little tree cover, and that much of the land unit has high annual forb and grass cover, which is likely cheatgrass in this location, with upwards of 50% annual forb and grass cover in some locations. In the far northwest corner, we can see that there is a pocket of higher shrub cover and higher bare ground cover. The vegetation conditions and trends table provides estimates of average vegetation cover and vegetation production across the land unit for the current year, in this case 2023, in the current conditions portion of the table, and the Thiel-Sen slope trend during the period of record, 1986 to 2023, in the trends portion of the table. In terms of current conditions, we can see that in 2023, there was an average of 650 pounds per acre of herbaceous vegetation production across the land unit, with more than half of that coming from annual forbs and grasses. And the trends show that annual forbs and grasses have been strongly increasing during the period of record, while shrubs have been declining. It's important to highlight two important considerations when interpreting the trend values and trend lines in this report. The first detail to be aware of is that the trend statistics are calculated based on spatial averages across the land unit. So in cases where the trend is near zero for a given vegetation type, there will often still be areas where the land unit is trending upwards and others where the land unit is trending downward, even if on average there is no trend. The second detail is that we do not calculate significance in terms of trend, so care should be taken in interpreting trend values. Further investigation can be conducted in the Climate Engine web application at app.climateengine.org, which enables users to produce trend maps using the Rangeland Analysis platform. These maps can help to account for variability in trends over land units, and there's also functionality to mask parts of the map that don't satisfy a statistical significance threshold. We encourage you to use the Climate Engine app for advanced investigation. The vegetation cover time series and vegetation production time series charts provide largely similar information to one another. Let's look closely at these figures since there is a lot to discuss. As you'll see, annual forbs and grasses, perennial forbs and grasses, shrubs, trees, and bare ground are all represented in the vegetation cover time series, and annual forbs and grasses, perennial forbs and grasses, and total herbaceous production are presented in the vegetation production time series. You'll see that multiple lines are represented within each figure, which provides information on averages, trends, and spatial variability across the land unit. This is much more information than you'll receive from most other tools, and soon we'll unpack why this is useful in management contexts. In the annual forbs and grasses chart in the vegetation cover time series figure, the red solid line represents the spatial mean and the red dashed line represents the spatial median. These statistics indicate the average across the land unit, but when they diverge from one another can provide useful information. For example, notice that in the years between 1995 to 2010, the mean value is somewhat higher than the median. The mean is more sensitive to outliers, so this indicates that there were parts of the land unit that had very high cheatgrass cover that were dragging up the mean relative to the median. In the years since 2010, the mean and median have been relatively similar, possibly indicating that cheatgrass has more homogeneously infilled across the land unit. Also in the annual forb and grass cover chart, you'll see the red shaded area displaying the interquartile range. This is a useful way of visualizing spatial variability of the land unit through time. The interquartile range shows the spatial 25th to 75th percentiles, and in this unit, the interquartile range is pretty narrow in terms of annual forb and grass cover, and that's because the annual forb and grass cover is relatively homogeneous across the land unit. If we compare that with another example land unit, we can see that although these two land units had similar average annual forb and grass cover of around 32.5% in 2023, the interquartile range for the second example is much broader, indicating more variability across the land unit. To drive this point home, we can look at the maps from 2023 and time series figures of annual forb and grass cover for our two examples, and we can see in each case that there is more uniform cover in example number 1 and more variable cover in example number 2. This is crucial information for management, as you will likely manage cheatgrass invasion much differently in our second example, where there are pockets of both low and high cheatgrass cover, from our first example, where there is consistently relatively high cheatgrass cover. Where the mean and median lines can help us to account for how a land unit is changing on average, the interquartile range can help to account for how spatial variability is changing through time. The last line that you will see on the annual forb and grass figure is the dashed black line representing the trend. Here we use a Thiel-Sen slope trend calculation based on the spatial mean, which is consistent with how we calculate trends throughout the reports. The Thiel-Sen slope trend is a non-parametric calculation, meaning that it is robust against outliers. The trend displayed in these figures has the same slope as is quantified in the trends portion of the vegetation condition and trend table. Together, these different statistics provide a wealth of information about each land unit in terms of averages, trends, and spatial variability that will help you to interpret vegetation condition and trend over nearly 4 decades. The Climate and Drought section provides 3 different summaries. The summary table and water balance time series figures both provide information on precipitation and evaporative demand. These 2 variables comprise the water balance of our land unit. It's important to note that it isn't necessarily bad if there is more evaporative demand than precipitation. In fact, most Western ecosystems are adapted to this kind of aridity and to seasonal weather patterns. However, if precipitation or evaporative demand has been trending in a certain direction, that could have significant ecological and resource implications. In our first example, we can see that in the summary table, there is an average of 9.16 inches of precipitation and 48.78 inches of evaporative demand during the water year. Importantly, both precipitation and evaporative demand have been increasing over time. The water balance time series figure displays annual summaries of precipitation and evaporative demand for each water year from 1986 to the present year. The solid lines show the annual data and the dashed lines show the trends, with the slope of the trend in the figure being equal to the trend value displayed in the summary table. The drought time series shows the long-term and short-term drought blend for each year from 1986 to 2023, and we can see that for this land unit, there have been regular fluctuations between drought years and wet years. Let's look at an example land unit from a much more arid environment. Notice that in this land unit, there has been a downward trend in precipitation and an increase in evaporative demand between 1986 and 2023, and that the drought time series figure indicates that drought conditions have been fairly consistent since around 2006. Perhaps unsurprisingly, both perennial forbs and grasses and shrubs have been declining during the same period. Let's look at one more set of reports to further investigate another important resource issue and to further develop understanding about how the site characterization reports can be used to account for vegetation change through time. In this example, we'll look at how tree cover has changed over nearly 40 years in two large land units that have very different spatial patterns in terms of tree cover. Satellite data is especially useful for assessing changes in tree cover through time because tree cover can change substantially over the period of decades, but can be difficult to measure systematically using field methods alone. We'll first look at a location with high variability in tree cover across the land unit. Looking at the map of tree cover and shrub cover, we can see that tree cover dominates the southwestern half of the land unit, while shrub cover dominates the northeastern half. Because tree cover has such high spatial variability, this is a great example for looking at the time series indicators of spatial variability. When we look at the tree cover time series figure, we can see immediately that the interquartile range is large. The 25th percentile has nearly 0% tree cover, while the 75th percentile approaches 30% tree cover. We can also see that the spatial mean, median, and 25th and 75th percentiles all appear to be increasing through time, with the tree cover trend indicating a 4% increase in tree cover averaged over the entire land unit. Notice also that the 25th percentile of tree cover is beginning to increase above 0% toward the end of the time period. If this continued, it could be an indicator of trees growing in areas that had not had tree cover during the satellite record. Conversely, we can look at another example with relatively low variability in tree cover. Notice that in the map, the land unit is covered fairly uniformly by around 30% tree cover. Similarly, the tree cover time series plot has a narrower interquartile range, indicating fairly uniform tree cover. Tree cover also appears to be increasing in this land unit. Accounting for spatial patterns in tree cover and how patterns have changed through time is essential for managers across much of the West, and satellite-based vegetation datasets have an important role to play in those assessments. The site characterization reports provide a wealth of information on vegetation and climate that can be useful for informing management. Even still, care should be taken when using climate and satellite-based vegetation datasets, as ultimately they are models of complex systems. These reports will be most useful when used alongside additional lines of evidence to inform decisions, such as field-based vegetation, ecological sites, photo points, local climate stations, and other locally available sources of information. Together, these different information sources can help to form a more comprehensive picture of a land unit and its history, providing a firmer footing for informing decisions. For more customized analysis of the datasets presented in the site characterization reports, you can use the Climate Engine app or API, both of which you can learn more about at climateengine.org. The Climate Engine app has been supported continuously by the Bureau of Land Management since 2015 and is built on Google's cloud computing platform, Google Earth Engine, allowing for rapid analysis of decades of climate and satellite-based vegetation data. Thank you for joining me for this video on the Bureau of Land Management Site Characterization Reports. This video is accompanied by a tutorial article at the Climate Engine support site at support.climateengine.org, where you can also find additional help resources. If you have any questions about the site characterization reports, please contact us through our support site where we'll be happy to assist you. Thank you, and see you next time.